And we are up and running. Welcome everybody to the July 13 Propeller Live Forum. We don't have a set presentation for today, but of course we'll have an update from Chip. One of the things I wanted to mention is that the incredible amount of work that is taking to just keep the products in inventory. We have been spending hundreds of hours getting components, sometimes replacement components, redesigning PCBs. So you will notice if you go to order, let's say the Propeller to the easy board or the 32 megabytes one, sometimes you will notice that the revision keeps increasing, and that's because sometimes we can do a drop-in replacement, but sometimes we need to redesign a section of the PCB, which triggers that we need to keep increasing the letters. So right now it's strange, but this week we finally got to the point that we have all the parts and all the PCBs, everything in place, and we are finally running the pick and place machine a little more smoothly. Sometimes we do have to run some inefficient short, maybe 50 boards that we don't like to do that. You need to set up the machine. It takes a lot of work to just set up the machine for 50 boards. And sometimes we need to do that. So there's just a lot of work behind the scenes. So when you go to the website and click in the shop area, you see the boards are there. Well, it was not easy to keep them there during this supply chain shortage. So, but we're doing good now. And the Propeller chips also, Propeller 1, Propeller 2 are in inventory. We are receiving next week about 13,000 Propeller 1s that are going to testing. So things are still in the pipeline and a little smoother at Parallax these days. So today we have an update from Chip on the debugger and maybe some other things. So Chip, I pass it to you.
All right. Let's see here. Okay, so I'm going to take over screen sharing, right? So let's see here. Oh, here we are. Okay, so here's a little program. You guys can probably see this okay?
Yep.
Okay, so two programs are going to run when this executes, right? There's going to be this here, some spin code that just runs in a loop. It just increments pin 0 through 7. And this launches a little Pasm cog to run this code here. And so this is going to start up two debugger windows. One is going to be running a Pasm program. One's going to be running the spin code. So I'll hit Control F10 to run this, and let me expand this a little bit. I have two windows going here. Let me move. This is the top program, the interpreted program is in here. And I don't know where this was last time. I think I had these down in the corner, but I've got all this stuff worked out. Can you see at the bottom, there's like hints that pop up as I move around? So this kind of makes it easy. I mean, it's pretty self-explanatory. This thing is, as you move around, the hints tell you what you can do.
They are not showing Chip on this side.
Do you see them at the bottom of the window?
Well, if it's in the hub line there, we can see them.
Yeah, yeah. This is the hub. This is a tab that says this is the hub. But this little window down in here, stuff appears in, right? So as I move around, tells me what'll happen if I click and what the meaning of things are. So this is the interpreter that's running here. You can see that X byte's enabled. Well, if I go here, it tells me that the X byte mode, it's an 8-bit mode. It's compressed for AO to FF. C and Z are affected. So I did a thing where with this little hint window, it allowed for a lot of nice elaboration on things that would be too hard to express all at once in that little box up there. But anyway, you can select what you want to break on. These are all your breakpoint sources. And right now it's just mutually exclusive. You press select one, any of them, but it's just one at a time. But the hardware is capable. I might make it so that if you left click now, it picks the one you want. But I might make it so that if it right clicks, it just toggles that option off and on. So you can actually have multiple break conditions. But right now it's just one. We can see where we are right here. Whoops. Let's see. Okay, so right now the thing broke at 236. If I go to main, I can then single step. I've got to fix this scroll thing. That's not right. I was up late last night working on this. Anyway, you can see instructions that will be skipped. And there is a break instruction here. If I say just break on debug, this is going to look, the disassembly looks the same every time because it's breaking at the same point in the program. But I could hit auto here and it will automate those breakpoints. I can also switch to like main single stepping and it will single step through everything and show you where you are in the cog, in the reg or the LUT memory.
What does auto actually mean there in that sense?
Just so next is like single step, right? Auto means just repeat. So it just kind of animates as if you're clicking step over and over, or as if you're clicking next over and over.
So it's kind of a slow motion run. Basically.
Yes. Yes. I don't know if it's a little too fast to watch what's happening, but it might be useful for some things. But I thought it'd be good to be able to have some animating, because you can watch, like if you look in the LUT and the reg, you can see, where it's running.
Is it possible to create a breakpoint, like if this value in the LUT changes at all, or if it changes to this break? Is that something like that possible?
It's not. You'd have to, because all we have in hardware are these things here. We can break on an interrupt entry or the main or the interrupt code. We can use an address breakpoint or any main instruction. We can break on an event, like see, I can say QMT and click that, and it would only, but that event's never happening, right? So it has a thing, you can just do an asynchronous break and it'll just tell you where it was. And I can just say, okay, whoops, maybe go back to here and just auto. To set a breakpoint, to use this, it's never going to hit 0. But let's see, let me bring the other window in here. This is the smaller program we had, right? The Pasm program. It has a break. Okay, let's see. So I'll go to single step, and this break #0 up here. This actually means go into the debugger. If that were break 1 through FF, that would mean do a debug message for like a plot window or something like that, or just a general message to the console down, this thing here. But if we single step this little program here, this is going to do a wait. It's randomly writing hub memory, and then it's adding to 100, 101, 102, 103, loops back. I can just have it repeat. So you see these little registers up here? It notices when things are changing in the cog registers, and it keeps track of changed registers. You can click this at any time to reset it, and it will, start keeping a new list. So as your code executes, anything that changes gets shown to you right here, and it prioritizes everything. So if it's something just changed, and there's something, and the list is full, but there's something on that list that hasn't changed in the longest time, it'll swap that out with the new value. So, because it's important to know what's changed as you execute. And see, this is not a symbolic debugger at this point. It's purely, binary. It's just looking at registers. It's disassembling just from machine language to kind of, raw assembly. And to set a breakpoint, like if I want to break on this instruction here, I can right click it, and that'll set the breakpoint to 8 and enable it. So if I say next, if I keep hitting next, it just keeps showing us what happened after it hit the breakpoint. I can hit auto, and then it will just, every time it gets a break, every time it hits that breakpoint, it updates the display and then re-executes. So this is actually something that the auto is useful for, because single stepping happens too quickly through code. But if you want to cycle through breakpoints and see what's changing where, this is useful. You can also, like we see that these are changing here. I could go down to here and just click on this, and then it will just stay there. So we can rather than show our code executing, it will just lock on that section of registers and show us those values, which are also up in here, right?
What's happening in the bottom right? It looks like pixels are starting and then fading. What is that?
Okay, so the program here is randomly writing data. Well, it's randomly picking addresses and writing data to the hub memory. So it's writing the value in 100 to some random location. So here it's getting a random value into pointer A. Here it's writing 100 to where that thing points. And here it's doing, I think, a delay of maybe 100th of a second or something. So what's happening down here is this is like a heat map showing where the changes are in the entire 512K of hub memory. So if we go to one of these dots here and click it, let's see. Okay, there, see that guy had changed at one point. See where it says DD? So as your program runs, it's going to be affecting hub memory. In fact, let's do this. Let's go back to this window, actually back to the source. And let's see, here we are. I'll not launch this other program. So we're just gonna run the spin code, right? This is all that's gonna execute right here. So it's gonna hit a debug interrupt each time through the loop. So Control F10, I'll run that. And here we are. Let's see. Okay, so now we're running the interpreter. And let's say we just want to keep tripping on that debug thing, that'll be faster. So right here, you can see that little yellow. There we are. I can click on that and hold it there. So we are seeing now what's changing in hub. So it kind of brings your focus to where things are getting affected in hub memory, because there's a lot of it. And depending on whether you're running spin, you have some stack activity like this, or if you're doing some graphics, you're going to see a lot of changes all the time. But it just helps you find where the action is. Then if I click here, it'll go back to this kind of display. And if I single step, these dots are going to light up only periodically as it loops and changes something on the stack. So right there, it's changing that to 23 next. Any questions about this or comments or requests?
I mean, the obvious one is to import labels from the compiler.
Yes.
Because being able to see the memory is not very useful if you don't know what's going on.
Right.
Especially if you have a spin program, you may not even be terribly aware of how everything's laid out in memory.
Right. I don't, it's not a sure thing to contextualize what's happening to any particular source code, because you could have self-modifying code, you could have overlays, all kinds of things could be happening that could cause a lot of misrepresentations in the disassembly.
Yeah, I mean, you could, but in those cases, you could just not. Whereas in most cases, you do have a particular thing at a particular address.
Right. Yeah, in most cases, you do, but what I'm thinking, the way I'll handle that is I'll allow for, at least for a first pass, so that you can give it a list of labels, right? And it will use those in the disassembly, and it'll let you see things by name. But I think it's going to work best if you pick a limited number of labels that are of interest to you, and then use those rather than pull in everything, because it'll be overdoing it. It'll be putting labels on things that, you know, aren't really what they appear to be. So how would you feel about that? Like having,
Yeah, just being able to select the labels that are interested. Usually,
Yeah.
you don't want to look at everything. You just want to look at particular thing. For example, I have, I've been having some funny thing with the audio registers in NeoYum. Something's weird's going on with them. So I would maybe put those, want to watch those on the hub and see when they get changed,
right.
because something might just be writing over them or something.
Yeah.
Very strange things occur with that. Well, it may also be some sort of actual issue where it takes the intended write path, but just writes garbage. I don't understand.
Yeah. Yeah, it's a tough thing in this architecture because we don't have like ROM programs. We have programs that are totally dynamic, and it's not clear. I've thought a lot about this and trying to use some kind of like algorithm to sort of figure out what the most likely fit is for your code back to your source code and use labels on those bases. But I don't know if that's, usually if it gets that complex, it's not the best solution. I'm kind of thinking now, because this is like a very low level debugger. If anyone wants to use this thing, they have to kind of know something about assembly language. So I think giving them like, you know, a budget of so many, you know, labels that tend to be smaller in name would suffice for debugging and wouldn't create a big mess.
Yeah, it doesn't even necessarily have to be the actual label. You could just say this is the one, because you have a layout issue because when the label is too long. Actually, is there a maximum length on labels? Is there any limitation?
32 characters. But see, in this little window, I don't want to have to like expand everything for the worst case all the time, because it would just take a lot of screen space, and I'm using a monospaced, well, we kind of need a monospaced font, but
Could you use maybe tooltips or something? Like just have a little indicator to show that there's a label here, and if you float the mouse over it.
Some sort of ellipsis thing, yeah.
Yeah.
yeah. Yeah, you know, now that would be pretty easy. I mean, something where if you touch 1D4, it tells you what the name is. Then it kind of reverses the query, which is better because it's not automatically doing the wrong. It's not going to automatically do what could be the wrong thing. You might say you might point to 1D4, and it could give you a list of like a bunch of stuff that compiled to 1D4.
Yeah, and if you just had some sort of indicator, like a box around it or something that indicated that there's more info here if you float, that would be helpful.
Yeah, that I could see that. Yeah, that's a good idea. I hadn't thought of that. I'm kind of thinking like the way I would use something like this is I would have maybe max. This is the kind of thing some people would hate, but I'd say like, okay, you've got a bunch of names you can enter in for locations, but you're limited to maybe 4 characters. You know, which is enough to get away from this mystery, like what's at 1D4 and what's 1D5, but it would be it would conserve on screen space because things could get big and sloppy quick. But reversing it, like you said, would help that, but it still doesn't let you see at a glance.
Or you could press a key to switch between numeric display like this and like label display.
Yes. Yeah. There's
actually, yeah, and with the label display, you could have it show just the first 3 letters unless you float the mouse, and then it extends to the right and shows the full label.
Oh yeah, that would be good. That would kind of solve a problem. Yeah, I like that idea. This thing's going to evolve a lot, I think. And
oh, sorry, just wondering how we would get the label addresses into the debugger.
We would have to have some kind of syntax for that when you issue the debug statement.
So are we integrating the debugger with Peanut then?
Yeah,
can't we
right now
use-
it's in Peanut, but anything I do here will automatically flow into the Propeller tool.
Well, I'm just wondering about other languages, like, you know, how someone could debug a C program, maybe.
Ah, yeah, I don't know. I mean, it's like this. I've been playing around with this thing for months, you know. This is one of those things that could like go so many directions, and it's hard to wrap up. I spent a lot of time just kind of distilling this format, trying to make it so that, okay, on each breakpoint, you can see all changes in hub memory. You're notified where they were. So that's a value, because 512 kbytes is a lot of space. So this little thing does that. And then here's a breakdown of the pins. Here's some pointer stuff, registers that are changing, you know, a bitmap of the LUT memory. It's like a literal bitmap of the bits. So here's a lookup table. Here's some code. This is empty here. So
By the way, is this currently integrated into the Propeller tool, or is this a separate standalone debugger?
right now I'm running it in my version of Peanut. So pretty soon I'll release a new version of Peanut. I'll put it on the forums, and then probably, you know, once it's good, a few days later, we'll put it into the Propeller tool.
So currently the Propeller tool doesn't have this at all.
No.
Okay.
No. Yeah, this is something that's been brewing slowly.
I'm very excited about this because I'm very comfortable with assembly language. So being able to do this is like a whole new world for me.
Good. Yeah. I mean, what I was really thinking a lot about was, you know, it's a mystery when you're programming something. You don't know what the boundaries are in all this, but this thing shows you the boundaries. Like, this is all of my reg space. This is all of my LUT space. You know, here are the special registers in reg space. Here are all the events. Here's some pointers. Here's the stack. I mean, everything that can be shown right here is shown. I mean, this is everything the hardware affords in debugging is being shown right here. And it's all kind of, I try to make it compact, but if you can see everything at once, it's helpful, because it's just always good to see, like, visually, you know, how much room have I got left? And you know, what's my code looking like when it executes? And
Does it cost any cycles to be, you know, providing all this debug information? Like if you hit run, is it running at full speed, or is it slower because it's
no, so okay, so I have this I'm breaking on debug, right here. Okay, here's breaking on single instruction. So this way, it's with every instruction, it stops and it reports. It does another data dump, updates the display, and then goes and does the next instruction. But when you do like debug, it's only breaking when it gets to the debug. So everything in between is running at full speed without any interruption at all. So the breaks, like, you know, main means break on every instruction. This means break on int one entry. Oh, and I got a stack here because I don't have another cog. In order to bust a cog out of like something like this where it's running, we're waiting for something that's not happening right now because I don't have any interrupts, right? So this hint says to force an async break in this cog, another cog must be idling in debug. So you have to have some cog's attention to go tell the other cog, hey, to create a break in the other cog. So if I uncomment this thing again and run this, now I've got two debug windows running. Let's see. Oh boy, let's see. So if I tell it to do something impossible, it this time allows me to break because I do have another cog idling. So this is all peer-to-peer. You know, there's no central cog doing debug. Each cog that's doing a debug interrupt is having its own conversation with the host PC. But if one is off in the weeds and you want to do an asynchronous break, you got to have some other cog idling in the debugger that it can tell, okay, hey, use this mask and generate a bunch of asynchronous breaks. So that's how you break other cogs if they're not responding to breakpoints. So I have, you know, an additional debug window it's funny, I don't see it. Once we run this Zoom stuff in the screen share, my computer starts behaving a little weird. So I don't see the other debug screen, but it's there because if I say next, it does allow me to break. And then it tells me where I am. So every time we do this, we wind up at a different place because it told us, okay, this is where we are now. So we've now done an asynchronous break and we're at this instruction. So if I single step this, it's going to execute another X byte. See, X byte's all enabled. And because 1FF is on the stack. So when we hit next instruction, it's now in the next bytecode execution. Or we can just break on the debug. Does that all make sense?
So wait, you said it's in the bytecode execution. So does next step through the bytecode interpreter, or does it?
Oh yeah, yeah.
step?
Watch this. If we go, well, just to main, okay, I'll stop it, right? So wait until we have a return instruction. So I'll step, okay, there. You see that return right there? And you see how we got 1FF on the stack?
Yeah.
And we've got this little orange check. That means we're ready to go. So when this return executes, it's going to fetch this byte right here. This byte. It's the RF read fast. It's going to grab 44, which is a bytecode, and it's going to pick up that, which is like, let's see, 44. I think it would be down in this table. Okay, let's see. 44 is 226, right? So I think the next instruction it executes is going to be at 226. Yep, there. So this is, so it grabbed a bytecode, got a skip pattern. See how these lines are going to get skipped right here? And it's now executing that bytecode. And see, 44 is now behind the pointer. And so it looks like it's going to grab, it's going to get a 0. It's going to get this. That's going to advance. So I do next. Oh, wait, now it's going to do it. There, the 44 moved down one. Hold on just a sec, guys. What, sweetie? Oh, okay, thank you. Thanks a lot. So now it's executing bytecodes. Every time it hits a return, let's see, here we go, boom. Okay, now here we are, we're ready. And it's going to pick up a new bytecode and execute it again. So this is your code running in the interpreter.
Okay,
that make sense?
So next isn't an assembly language step, it's a interpreter step.
Well, it's just whatever. I mean, it all has to do with what you've selected here.
Oh, right. Okay. Yeah.
It's just it's the break. Right now we're breaking. We see main says this is going to break on every single main instruction.
And since main is in spin, there's spin steps.
Right. Yeah. So this is, I mean, everything ultimately that runs is assembly language, right? But there is this X byte mechanism that can pick up a byte and execute it by looking up a table with a jump address and a skip pattern, and then jumping to that address and setting up that skip pattern. Like, see here, it just got into here. Here's the skip pattern. So it's 0, 0, 0, 0. That means it's not going to skip where it's at. It's not going to skip this. It's not going to skip this, but then it's going to skip this whole spate of instructions. So we go next, next. Next thing it's going to be at is 230 because it's going to skip over all that other stuff. So boom, there we are at 230 RF byte. And here, this is the actual debug, the break instruction. And it returns and gets another bytecode. So this is, I mean, if you made your own bytecode interpreter, it would look something like this. You know, you'd see it doing this. And then the other window, and let's see, where is it? Let me drag this one off here for a minute. Oh, I think it might be on the other screen. Hold on. Oh, got hidden behind everything else. Okay, so here's the other one. This is the cog that just has this simple little assembly language program in it. Let's see. Wait a minute, this still is the, what is going on here? Let me start this over again. Let's see, is this our, okay, here's our Pasm program. This is it right here. So this thing, if we look at the code here, this is 0, right? This is 1, and then it's going to add one to a couple registers. It's not gonna do this big delay, and it's gonna jump back. If I pull this big delay out here and run this with the debugger, then okay, here we are. So we say run main code. Wait a minute, this is not the right cog. All my windows are a little jumbled for some reason. Hold on a sec. Okay, here we go. Okay, here is our Pasm program. Okay, there we are. So whoops. So we can single step. Now, if you're writing Pasm code, you're not going to have all this crazy jumping around from bytecodes, right? It's going to be a lot more linear. So here we have a big wait instruction. When it executes, the ogd is going to, these are going to execute together. So it's a long wait. It's like a 1 second wait. And it gave me the opportunity to break in there because it didn't know how long it was going to take. It took over like 100 or 250 milliseconds. So it figured, okay, I don't know if it's ever coming back. So I'll give the user the option to just do an asynchronous break. And then now it's going to execute this jump 0. It's going to go right back up here. So if we hit next, boom, it goes there. And then this is the thing that is the debug instruction. It's going to just skip that in this way. And it's going to write some random, oops, there it goes. Anyway, does that all make sense? Hope I didn't put anyone to sleep.
No, it seems to make sense.
Okay. Yeah, so you can execute any, I mean, and you can run, you know, you can debug all 8 cogs at once. There's no limit because each cog is having its own conversation with the host PC. The only thing is if you want to asynchronously break one cog, you got to have some other cog that's, you know, creating routine debug interrupts so that it can be handed the request to do the async break on the other cog.
Hey,
But
Chip,
otherwise, they're all independent.
what's the earliest version of Windows that will run this?
Well, I have a Windows 8 machine here, but this is written in Delphi, like I think it's the, gosh, let me see, let me look. We're using an old version of Delphi. Here it is. Let me, let's see, about, so this is from 2001. So it should run on very old Windows. I guess it would be compatible with at least Windows 2000.
And what kind of performance do you, what kind of level of system do you need to keep up with it?
Oh, I don't know. I mean, not much. It's the way this thing is working. Let me try to get my window back here. Is I didn't use any like Windows controls, right? Because when you start using all those Windows objects, it creates all this execution with all these delays and all this stuff goes wrong. So the only event I'm using is mouse move and mouse down in the Windows API. So you see, there's a lot of stuff here that's like you don't see focus changing really, like as if you were hitting tab and, you know, dark outlines move around. This is all just totally raw. So I maintain a bitmap that is the screen here, and I promote that to the canvas that's visible, you know, on your display. And all I'm doing is tracking the mouse and the mouse clicks. That's it. I'm drawing everything. Every time the mouse moves, I check to see, is it in this box? Is it in this box? So these are some really simple little math queries that don't involve any kind of API calls, right? It's very, very simple. So this will run really fast, I'm sure, on an even very old machine because it's not stacking up all kinds of Windows events. Does that make sense?
Yeah, that makes sense. And so if Is there hardware lines between the cogs so that any one can break any other one?
Well, any cog can issue an asynchronous break using like an 8-bit pattern. So that 1 bit is for each cog. But the thing is, they can only issue that if they themselves are in a debug interrupt. So it's kind of like this alien abduction scenario where cogs in their waking mode don't know anything about debug. They cannot access it. They can't control it. They're just running user code. But once they're in debug mode, then they can do special things.
So is it somewhat like supervisor mode?
Yeah, you could, I think, yeah, you could call it that. It's pretty simple, but it's enough. So I made it so that nobody could like exploit debug features for any kind of runtime purpose. Now you can, if you want to totally forego being able to debug like this, you can use all those resources. But for normal programming, I didn't want to make it so that anybody could like, oh, there's this cool trick where if you do this, and then you get this, but then it blows up debugging normally. I made it so there's like a separation between them so that when you're in the debug mode, it's like you're in the alien mothership and your conscious doesn't know what's happening, but other things can happen. Then you go back and you resume what you were doing like nothing occurred. Does that make sense?
Kind of. I'm going to just have to play with it to get my mind wrapped around it.
But it's kind of like, I think you could liken it to supervisor mode. It's just something that, you know, it's separate. I mean, you're still executing instructions, of course, but certain instructions do different things in debug mode than they do in normal execution mode.
Just out of curiosity, is there going to be documentation along with this? Because this is a fantastic debugger, but it's also kind of complicated. So some docs might be nice.
Yeah, yeah. I'll add to the spin 2 doc, and yes, I'll cover the stuff. I mean, all you got to do, you know, normally debug, you can put things like for messages, you might do something like this, right? There's all kinds of stuff. We have all these like debugging graphical windows and everything that use that you basically use this. But if you just say debug all on its own, you can do that, you know, in Pasm right here or in spin up here. If you just put a simple debug, it just drops you into this debugger.
Actually, that was one of my questions was how can we access the debug tools from Pasm? Because I'm doing most of my work in Pasm, so I want to.
Yeah, just type this,
Okay,
and
awesome.
that resolves to a single instruction, which is, let's see. Oh wait, it's here. Hold on.
But what does that do with the propeller tool? Anything, or do we need Peanut for that to do something?
Well, so right now you need Peanut because this kind of like expanded what the whole debug conversation, how it works. Basically, when one of these, like when a debug interrupt occurs and it eventuates in updating this window you see, what happens is the first thing that gets sent out is the cog number, which is 0 to 7. Well, that's an illegal ASCII character, right? I mean, it doesn't normally mean anything. It's not a printable character. So when the thing that's like, what would you say? It's like dispatching, you know, where debug messages go. When it sees a 0 to 7 come in, it goes, okay, no one else is going to know about this. This is like a quiet conversation. It doesn't wind up in this window, right? But a little conversation ensues that begins and ends in like 5 milliseconds, 2 to 5 milliseconds. And that is, you know, it gets all this checksummed data for the hub memory. It gets all this stuff here, all this memory. And then it releases. So you can see that this counter is still counting, right? Even though we're kind of sitting on this one instruction. It's because many debug interrupts are occurring. So if we're not stepping, if we're not doing anything like this, the PC just sends out a little command saying, okay, call me back in like 64 milliseconds because I'm waiting for the user to press a button and I don't know what he wants to do yet. So right now it just keeps giving the callback. Just get back to me in 64 milliseconds. So in those interstitial times, all the other cogs can keep sending debug messages that might go into plot or scope windows or logic analyzer windows or whatever else. But this conversation is kept, you know, off the radar of all that other stuff. And all these debug interrupts, they start and end in a couple of milliseconds. So you're not like tying up anything else that needs to do any kind of debug, be it a debugger interrupt like what you see on the screen, or some kind of you know, graphical debug window that's showing some data. Everything just keeps running. And by spacing them like 64 milliseconds apart and having them all take 5 milliseconds or less, you could have every cog doing what you see here on the screen without taking any bandwidth from any other, because 64 milliseconds over 5 milliseconds is almost 13, right? So 8 cogs, there's still time gaps in there where nothing's happening. That makes sense?
Yep.
It's designed to be like really quick. So when this debug interrupt occurs, you don't even know that what the user wants to do yet, but you just update the data. And if the user did click on something, then it gives that back in the next time it comes around, probably, because it doesn't wait for anything. Because if it were to wait, it could wind up holding up all the other cogs from being able to do just regular debug messaging, or which would translate into like an execution stall that's chip wide. That everything happens in just these little bursts. So there's lots of interstitial time for everything else to happen.
You say the command to trigger it is debug without parentheses. Now, Eric has his mic muted, but I can already hear him screaming because, dear God, the debug is already like giant mess to pass.
Wait, explain that. Say that again, Ada.
Just a slightly humorous comment about the pain of parsing the debug statements. That's the other guy who wanted to talk back about.
Do you mean like
parsing the thing?
The complexities Eric will face if by putting this into? Is that what you're talking about?
Among other things, because normally the symbol without parentheses would be a function call, but with with empty parentheses.
Oh, you're wondering how are we going to give it labels?
I'm just thinking, because normally if you wait, the debug without the mixed brain hurt. See.
I think just having a single debug with nothing else probably isn't too bad.
I guess you could make a separate rule for debug without parentheses.
I think
it's already
so.
A keyword, right?
It is, yes.
Okay, so I thought for a second I thought it went to the normal function call handling, which don't think it is.
No, yeah. See what happens.
But it's kind of, there's no point. FlexBin can't talk to Peanut. Like, this is all, you know.
Yeah, but it can generate a break 0, and and you can load that with whatever.
Well, we don't have this debugger screen.
I mean, if it's in Peanut, you can just tell Peanut to load the compiled binary.
No, that would be nice if Peanut could do that.
I think it can.
If Peanut can do what again?
Load a compiled binary with a debug stub attached to it.
Oh, yeah. Yeah. I mean, so for your information, you see this break instruction, break #0. That is the debug if you're in assembly language, which you would always be, Eric, right? Because everything.
Oh yeah, no, we can compile the debug statement into a break #0. That's fine. The problem is that then we would need Peanut to be able to load the binary that we've constructed.
Right. Yeah, that would need to be done. The code to do this isn't that long. This whole debugger here is like, let's see. This is the entire debugger, right? Whoops, let's see. Hold on. Oh, wait, I've got let me get this thing all the way over. So it is, this is all in Pascal or Delphi.
It's all in Delphi, which, yeah, would need to be translated.
Yeah, so the whole thing is 2,340 lines. And of that, you know, the shape, the anti-alias shape drawing and line drawing, I put that in here, but modified it for this context. So really, aside from the shape drawing stuff, the debugger is 1,811 lines.
What happens if you run a compiled binary with debug in it and it can't talk to Peanut?
That would work. I mean, if you're just loading a binary and it's going to be generating, oh, wait a minute. Okay, Eric, there is a little more we have to do. We have to have the debugger initialization stuff in there, right?
We can compile the whole debugger, like everything. The way it works right now is that we compile the debug stub along with the user's binary to make
Okay.
what
all right,
downloads.
so-
I assume it's what Peanut probably does something similar internally.
Yeah, it takes the user's binary.
No, Peanut just has a precompiled blob and then just appends that.
Yes.
Well, it generates the table and then appends the blob.
Right.
Right. It takes the user's code and then appends to it this pre-run thing that sets up the debug. And then it runs. And then when it gets these debug interrupts, these break instructions, then it jumps to the code that's in the high 16K bytes of RAM that's write protected.
Yeah, we know how this works. We know how it works.
Yeah.
The only difference, as I said, is that FlexBit actually compiles it at real time, which kind of causes more issues than it actually solves, because the actual source code is inside the binary, but it compiles it because reasons.
Right.
I think that was just the easier way to do it.
Right.
So this goes into special memory that cogs can't overwrite, and it's not part of the hub?
It's part of the hub. So the hardware we have a megabyte of address space, right? But we only have 512K of RAM, but the architecture set up so that you can always take whatever the last 16K bytes of that RAM is, and you can map it to FC000 to FFFFF. You know, you can take that last 16K and it'll disappear from the end of the normal memory map, and it reappears at the very end of the full 1 megabyte memory map. And it can only be, once protected, it can only be written from within debug interrupts. It's like when the alien abduction is underway, it can be modified, but normal code cannot do anything to it. It can look at it, but it can't affect it.
So if you fully load the chip, is it 512 plus 16 kilobytes in the binary?
It's 512K minus 16 if you're using the debugger, because the debugger needs that last 16K of memory to do all of its stuff in. And most of it is just buffer space, you know, for when you're in this context that you're seeing here. We've had to unload what was in that cog, store it in that memory, and that's 2K bytes anyway, not much. And then we had to reload in the debug program, which also has overlays that can come in. And then when we're all done, we reverse everything and restore the cog to its prior state, and then do a return from interrupt 0, and then it starts back up from where it left off. In fact, if you look here, like in the reg space at the very end of memory, this is ROM code, like from 1F8 to 1FE. When the hardware jumps here, when it gets a debug interrupt, see, this actually saves off. Now, this is not you can't do this in normal code. You can't say minus cog, you know, shift left 7, but this is what the hardware does on a debug interrupt. So it kind of like dynamically saves it off to that cog's buffer. So here it saves it. here it reloads. Now it reloads a little 16 instruction program, and then it jumps to it. And then that thing will save off the rest of the memory. And then when you're finally all done and you've brought everything back into memory except those first 16 locations, this cleans up those the first 16 locations by reloading from the original save buffer. See FF80 minus cog, FF80 minus cog. It reloads and then it does this return 0. And oops. And then you're back where you left off on your program. But see, this is all instruction ROM. Notice this data here is actually like IO pin stuff and pointers, right? But if you were to jump here to execute, this is what what the cog would execute. It wouldn't execute this stuff because it knows this is data, but there's like a special 8 long instruction ROM in each cog just for getting in and out of debug. And I have it in here so you can see it.
So it's similar to pushing the whole cog's memory off to stack.
Yes. Yeah, it saves
Going
everything.
And then popping it right off the stack and then executing the next instruction.
Yeah, but it's not using a stack. It's using like an area in that 16K of RAM that's been remapped to the end of the 1 megabyte space. It uses that. And see, the thing is only one cog. Now, if you look here, we've got like 2 of these things running, right? We've got this one, we've got this one. Only one of them is actually in the debug interrupt at any given time because it's only like max a 5 millisecond deal. So one of these guys is using, the store space to store this, right? Here's one, and then here's the other, right? So depending on who's in the interrupt, one of these guys is using that storage space. So when it uses the lock 15 as a semaphore to like say who gets to use the serial ports next, it also says who's going to be able to use the big buffer space, the 2K buffer that has to hold the context of the whole cog. Not the LUT. The LUT never gets touched, right? But the cog, the register space does. Does that all make sense?
So when you're debugging multiple cogs, it flips back and forth.
Yep. Yeah, this stuff's switching in and out really rapidly.
Okay. How many cycles does it take to go?
Well, okay, so
from running cog to the debugger.
It's not that long, but remember, every time a debug interrupt occurs, it has to do checksums on the whole 512K minus 16K of hub RAM. So the code that does that, I'll show you. I mean, I made it so it's like as quick as I could, because tallying up 512K bytes of memory is not trivial. I mean, it's simple, but it's so here, let's go to this code. See this code right here? So this is inside the debug code that gets loaded into the cog after what was in there gets swapped out. So here it reads 16 locations, right? Which is 64 bytes. Then dealing with like 32 bits at a time, it does this stuff. So for each long, it's taking, this is 2 clocks. Each one of these is 2 clocks. And then it took 1 clock to do the block read. So 3 clocks per long. So it's less than like 1 clock per byte. So it's maybe like 384,000 ticks that have to go by just to checksum the memory. So what's that? At 300 megahertz, it's a little over a millisecond.
And that's the checksumming of memory is so that you can detect which is changing?
Yes. Yeah, so that you can, yeah. Now see, if we didn't do that, then we could save some time, but there is like, we still also have to do checksums on, oh, let's see, where did I put it? We do a much more thorough, okay, the hub memory just gets checksummed in this kind of wonky little fashion. But for the cog, I use something a lot more strict because it's more critical. You really don't want to be wrong about cog changing or not changing because critical stuff's happening. So, oh, is it down here? Let's see. Where's my code that does, for the cog, we do a CRC. Let me just search for that. CRC nib. Let's see. Oh, wait, wrong focus. There we go. Yeah, so at the outset, it sends 64 CRC words for each 16 register group. And it does like a proper cyclic redundancy check, you know, using this code here. So those checks are like super thorough on the cog memory. On the hub memory, it's more kind of drive-by.
And so the whole process is like 500,000 ticks?
Yeah,
like that?
probably.
So
Probably.
it under 2 milliseconds?
Yeah, it takes, to do the whole debug in and out, it's 2 to 5 milliseconds. And so what happens is, when you first come into this debugger thing, you can see right here, it's like sends off the status, like, you know, what cog number is it? What are our special registers? What are our debug registers? And then it goes, sends off the checksums for the cog registers and the LUT. And then it sends off the big checksum, the simple, not CRC, but the simple checksums for the whole 512K minus 16. And then it gets the command, it gets immediately commands from the PC. And then the last thing it does is it sends back the requested register blocks, including LUT that might have changed. It sends off any 4K bytes that might have changed. And it got those instructions when it received these commands here. So the idea is, because USB has all these latencies, like these USB to serial things have all these turnaround latencies, right? So you want to have as simple as of a conversation as you can, because you don't want to be saying, oh, send something to the prop2 and then wait for the prop2 to respond, and then you send something back. All those turnarounds take a lot of time because of the virtual COM port running over the USB system, right? So it's just, this is all that happens. You get into a breakpoint. The P2 sends its checksums. Then the PC sends to it its commands, which you would think are going to be out of phase, but it knows what to request for elaboration on the literal, like what's in the regs and the LUT, and also what are the sub checksums on the main memory, and also what do you want me to tell you about the hub memory, because you get to query like you get to give it 5 different queries. And then the P2 turns around and just sends the requested data, and then it goes back to what it was doing. It gets completely back out of the debug interrupt and goes back. But it also issues like probably a, well, because the PC told it to, issue a call me back in 64 milliseconds command. So it gets in and out really quick. Does that all make sense? It's all about minimizing the conversation and minimizing the turnarounds to like 2. So it's P2 to PC, and then PC to P2, a very short message, and then P2 to PC, whatever was requested from that exchange. And then that's done. Then it's either back running code, or it's doing a 64 millisecond wait to get a callback later to find out, you know, does the user know what he wants to do yet?
Can it get much simpler than that?
Yeah, I really thought I had to really work this through thoroughly and kind of get it super ironed out and figure out everything I could do to get rid of every like contingency possible to just minimize the conversation and keep it fast, you know, fast but complete, so that by the time this little conversation's over, on your display, you have a completely up-to-date picture of what's in the registers and the LUTs, what the status of the cog is, and what has changed in the hub memory and updated display for whatever part of the hub memory you were looking at.
It sounds like the way you wrote it, small and simple, it would run even better on another Propeller too.
Yeah. Yeah. I would
You
like
wouldn't
to
have to
do
do
that.
latency stuff, and you could control your screen, and that's interesting. How big is it in as a binary
You mean, okay, what runs on
on
the
the Windows
P2?
side?
We'll say that again.
How big is the Windows binary just to do the debug stuff?
Oh, I don't know, but the entire application, let me see here. Let's ask it. It's less than a megabyte. It
And what-
could be like 300 kbytes if we could use a compressor, but these days Windows flips out if it sees compressed code because it thinks it's some kind of a virus or something.
What about the stuff in the P2? Like, how much of a overhead does Peanut require, or does it require any? Is it working just on
Well,
stuff?
Peanut doesn't require any overhead, but the debugger does. So the debugger sits, well, look here, I got a little map here in the top of my code. If we go back to this, so this is the code. See, it says spin2 debugger.spin2. So if we go to the top of this thing, here's the memory map. So this is the memory setup, right, for the last 16K. So this here is the buffer that will hold like the whole cog memory or the whole register space. Here's where the actual debugger sits, and it has some overlays. I should put in here like debugger plus overlays plus data. So what happened was the debugger didn't fit all in the cog at once. So I made an overlay area where I can just bring in stuff from the other part of this memory right here, right? Between here and here. There's, I don't know how much, I mean, what is, well, I can do the math here. Let's see, and pull up a calculator. Whoops. All right, we'll go to programmer. So we're like well, basically take the lower digits here. Oh wait, let's go to hex. COO minus 1AO is that, and then in decimal, it's about 2 point, well, let's see, divide by 1024. Oh, this thing truncates the fraction. So it's like probably 2.5K or something. It's not much. But see, here are all the little storage areas, right? Like when an interrupt occurs, like when cog0, when a debug ISR occurs, it saves the first 16 registers here and then loads a program into those registers from here. And then that program saves everything off, saves all the big stuff off to here. And then it loads in this stuff with overlays, and then it reverses everything when it's done. And then this business up here, from there to there, C, D, E, A, that's about 11K or so, 10K. That's all the debug stuff for like debug windows. It has nothing to do with the debugger, but it's all the data for like debug display windows, like plot and scope and bitmap. All that kind of business winds up in here. And that's like more or less textual data. But this stuff all, see, when the debugger gets attached to your app, all this stuff gets squirreled away in that top 16K and it gets protected. And then only on debug interrupts does it get accessed and can it be rewritten. So as far as the user program knows, the only thing he knows, aside from missing time, if he's paying attention, is that he doesn't have the last 16K of RAM is gone, doesn't exist anymore. He can read it, but he can't write it. No, actually, from his address space, it will disappear. He can see it at the end of memory. Like if we go to here, right, and we go, I can There. So there. So this is the beginning. This is where the distilled, debug stuff winds up for all your debug statements. And then it was at F. What was that address? F1AO. That's where the code begins. So FF1AO, if we go to here, there's where the stuff sits that gets loaded into the cog on a debug interrupt. And if I click on this here, boom, now we can see it up here. So this is the debug code right here. But no one using the debugger really needs to know. I mean, I like talking about it. I like it. But in practice, nobody would even really need to know this or maybe care about it, but that's just how it works under the hood.
Does it still use 63 and 62 for transmit and receive?
Yes.
So it's multiplexed or whatever with the
yes, it's time
other
multiplexed.
How does that affect what you set baud rates to?
Well, the faster the baud rate, the shorter the conversations get. So the only thing that would happen if you set a lower baud rate is it would take longer to, every conversation would take longer. So that would just slow things down. I think it's all it would do. It wouldn't cause anything to not work.
So your 2 to 5 milliseconds is dependent on what baud rate, like 2 megabits?
Yeah, that's at now 2 to 5 milliseconds is at 2 megabaud. And then right now I'm running the chip at 300 megahertz. So it would stretch out if you went to like 200 megahertz. It would get a little bit longer, because the comm times are static at 2 megabaud, but the time to calculate the CRCs and the checksums and the hub memory, that's all variable, and it doesn't always fit within the timing for the communication. So it can stretch it out a little bit.
What's the fastest serial port from P2 to P2 have you seen?
Well, from P2 to P2, it could be like tens of megahertz, but from the PC, 2 megabaud is like it can do 3, but it's touchy. And I think I was playing with 3 by cutting down the latency. Let me pull up the device manager on my machine here, and let's see. So what you need to do to cut those, remember I said the turnarounds in the conversation take a lot of time?
Yeah.
Let's see, advanced. Okay, so this is the USB, this is the FTDI thing, right? Go in here. Now, this is the big deal. This latency timer is normally set to 16 milliseconds. That means that anytime you turn the conversation around, you suffer a 16 millisecond delay because the PC is just not going to be looking fast enough. But it's all set up between this buffer size and this thing that at 2 megabaud, everything works. But to go to 3 megabaud, you absolutely have to cut this thing down. But I was finding that at 3 megabaud, it wasn't really that, there was still some unreliable things going on, even with the latency cut down to 1 millisecond. But I'm not remembering. Jeff at work, we were talking about this, but I just remember thinking that we just need to stick at 2 megabauds because 3 is, it's not reliable and it can't really be made to be reliable. And the funny thing is, if you use the API that FTDI gives you, all it does is puts this under API control. It doesn't give you any lower level access than you still have to set like the latency timer, and you still set the buffer sizes. I was thinking that the API would let you really get underneath things, but you're still basically stuck with the same settings you have, just configuring the serial port under the advanced settings, which is right here. You don't get anything extra. Does that all make sense?
Yeah, so why did you develop this on a PC and not on a P2 itself?
Well, that's what I want to do, is go to a PC because, to the P2 itself, because it's going to be really cool to be able to write software that never breaks again, because the PC is always a moving target. And over the years, you can't even give someone an executable anymore because their antiviral software will scare them away from running your code, telling them it's probably some kind of Trojan horse or something. So it'd be really nice to get away from all that. But it would mean that the person would have to plug in monitors directly to the P2 and keyboard and mouse. It's not a big deal. I have that on my desk, but I'd have to have it shareable between my PC and the P2.
It's basically making a P2 Raspberry Pi.
Yeah. Yeah. It'd be fun. I could take the whole compiler and write everything in Spin2 and make it all work. And then going forward, we could just make a Spin2 interpreter in C that could then run the whole compiler on any platform. All you got to do is compile in C the Spin2 interpreter, without the IO commands, just the memory movement stuff, and then some kind of thing for file IO. So you that are asking, you would like to work on a P2 and not on the PC?
Yeah, I hate PCs.
Say that again.
I hate them because they're too complex. Like you said, they move around. I don't run Windows typically. I run Linux. But even that,
But even Linux is a pain, you're saying.
Yeah, you've got libraries that constantly are updating, and I want to be able to pull out 10-year-old hardware 10 years from now.
Yes,
yeah. Just run it.
Yeah, that's what we've always thought too. It would sure be nice to be able to go back to a system years later and you pull up the same exact working environment. It's super snappy and quick, and you don't lose anything to this whole metamorphosis that's ongoing with bigger systems.
On the other hand, though, for software development, I love Git and having, all the high-level development tools. So there's an argument for both sides or both ways.
Right, there is. And who knows, maybe we could make a Git interface.
The thing is, this is a new thing. Windows used to be good, believe it or not. But at some point they fired their QA department, and since then all the programs start. I
don't know, that's arguable. I've been a Linux user for a long time, and Windows, even since back to Windows 95, has been sort of a weird contraption.
95 is a bit funny because it's basically just a DOS shell, but it kind of like eats the DOS from inside out, because the DOS drivers are like really slow because they're never re-entrant. So it kind of eats the DOS drivers from the inside out. It copies, it like hacks them to disable them and then use its own drivers. It's very bizarre, this operating system, but NT actually works good. Used to work good before they fucked it up. Now we have funny issues where APIs randomly stop working and just the computer randomly upgrades itself to a new operating system, and like the computer randomly refuses to run your binary because it thinks it's not secure.
Living in Windows is like living in an apartment. Being in Windows is like being in an apartment building where the landlord hates you and he's eventually going to kick you out. Just a
I'm still using Windows 7 on this. It's like, especially if you take into account the video capture hardware, which that's barely supported by Windows 7, because when Windows 7 came out, analog TV was on the way out. Then it runs the drivers on Windows 7, and the whole machine is an AM4 machine with Ryzen CPU, which itself barely supports Windows 7. It's like extremely funny setup that I have. I don't know.
Sorry, I was just going to say, Chip, if you're looking for suggestions or things that could help people, I'm a very experienced assembly language programmer, but I'm just basically starting to get into electronics, and the whole thing about the P2 is completely fascinating, especially like the smart pins and the different logic modes and stuff. But the big thing holding me back is documentation and just being able to move forward with different projects. Like, for example, there's in the Propeller tool, there's that chord program that or the chorus program that you wrote that lets you speak into a microphone and provide MIDI information, and it does something. But I have a headset with a microphone that even with the AV module, the microphone it's apparently not reading it or something. I don't know why. And also with the MIDI, you mentioned using MIDI, and there's a MIDI pin input, but when I look at the MIDI pinouts, there's two MIDI data. There's a plus and a minus, so I don't even know how to wire up my MIDI port to work. So a more fully functioning and working examples for the different features would be super useful as a launching point to getting people into the project, especially like me, if they're kind of new to things and they want to break into this.
Yeah, I understand what you're saying. Let me see about the MIDI being it's a dual signal, differential signal thing, but there's a little board I bought. I'm on Amazon. Let me see if I can find it. MIDI interface board. Here we go. Let's see.
Chip, as we are moving into general discussion, shall I stop the recording and we pause this part and then we just open discussion?
Sure, yeah.
All right.
Here's, let's see.